Our speaker for today is Dr. Mary Carroll. Mary is the Dwan W. Crichton Professor of Chemistry at Union College and the 2023 President-elect of the American Chemical Society. Mary has earned a BS in chemistry from Union College, a PhD in analytical chemistry from Indiana University, Bloomington, USA, and performed postdoctoral research at the University of Massachusetts, Amherst, USA. At Union College, she teaches courses in introductory and analytical chemistry and mentors undergraduate research students. She co-directs the Union College Aerogel Lab, a vibrant and productive interdisciplinary research group. In addition to fundamental studies, the group investigates applications of aerogels in sustainable buildings, chemical sensing, drag reduction, and automotive pollution mitigation. Mary co-founded the Shun-Through LLC to commercialize the aerogel technology developed at Union. Mary has been a member of ACS since 1986 and an ACS volunteer leader since 1993. She served as a counselor of the ENY ACS section from 1998 to 2022, representing the section at council meetings and participating in ENY executive committee meetings. At the national level, she has served on the ACS Committee on Science, the ACS Leadership Advisory Board, and served and held leadership positions on the ACS Council Policy Committee, the ACS Society Committee on Education, the ACS Women Chemist Society, and numerous working groups and task forces. Based on her contribution to science and service to the ACS, she was selected for recognition as a member of the class of 2016 ACS Fellows. Thank you, Professor Carroll, for joining us. The stage is all yours.
And thank you very much for the invitation. I'm delighted to be here, and welcome to all the attendees. First of all, I'd like to say Happy National Chemistry Week. In the US, we are celebrating National Chemistry Week this week, and so it seemed a very appropriate day for me to talk to you about some of the work that I've been doing in collaboration with colleagues and students at Union College. And the other thing I wanted to say at the beginning is I'm honored to be a member of the ACS presidential succession. I've very much been enjoying interacting with ACS members virtually, as we are doing today, and in person in various venues throughout the year. And I'm really looking forward to my presidential year that starts January 1st. So I'm going to share my screen. And we will get started with the presentation. And just to verify, is that working fine from your end?
Yes.
You can see it perfectly. All right. And this is just the title slide. I'm going to be speaking today about aerogel materials for sustainable building applications. I'm going to first spend a little bit of time talking about what aerogel materials are and how one makes those materials. And then I'll talk specifically about the application of these unusual materials to sustainable building applications. I will be focusing on work done in my own laboratory, but I will also be referring to the considerable amount of work that has been done by others. And so just to be sure that everyone's on the, sort of on the same page, what are aerogel materials? And they're nanoporous, low-density materials that are really very unusual. They are considered nanomaterials because they're nanoporous. They have mesoporous things. So typically pore densities are a variety of sizes, but the average pore size would be on the order of 10 or 20 or 30 nanometers. So they're not nanomaterials in the sense that the materials themselves are small. These are network solids, but that they contain a lot of pores. This gives them very unusual properties. And so you may have seen pictures like this, where this is showing a silica aerogel, so silicon dioxide matrix, and it is very strong in compression. It can hold up 1,000 or 10,000 times its mass. I should point out that it does not weigh very much, so it works pretty well in compression here. This is from the NASA Stardust mission. At the time, there was a record for silica aerogels made by the NASA Jet Propulsion Laboratory in California for the Guinness World Record, but that record did not stand for very long, actually carbon aerogels, and in particular, aerogels made from carbon nanotubes and graphene sheets, as far as I know, currently hold the Guinness World Record with a density of 0.16 milligrams per cubic centimeter. So the materials have a solid matrix and the pore with a lot of pores, and the pores are filled with air, hence the name aerogel. Now, as I just mentioned, they are among the lightest known solids. There is, of course, a range of densities depending on what material the aerogel is made from and via what process. But these densities, as you can see, compared to the density of air, are very, very low. And this gives unusual properties. In general, aerogels have very high thermal insulating properties. They have a network, and one can think of this network as each of these balls in the cartoon is not an atom, it's a cluster of atoms. So colloidal particles that connect together to make an overall solid matrix that is highly porous. As a result, there are tortuous pathways through this, and these materials tend to be very high in thermal insulating properties. Silica aerogels are also excellent acoustic insulators and electric insulators, though of course the carbon aerogels, if they're based on graphite or graphene, conduct electricity. And in this talk, I'm going to be focusing primarily on silica aerogels, which also have an unusual property in that they can be formed so that they are translucent or even transparent in the visible region, which opens them up to applications where one would need to be able to see through them. Aerogels have unusually high surface to mass ratios. Here I said up to 1,000 meters squared per gram, but there are actually aerogels that are higher than that. Silica aerogels tend to be in this range. And again, the majority of the pore sizes are in the nanometer region. Now, aerogels can be and have been used for a variety of applications. They've been known since Kistler developed them in the 1930s. And many of these applications either come from their insulating properties or their structural properties. And so for insulating properties, they've been used for things like blankets or coats, insulating coats for extreme environments, window panes, which is what I'm going to be talking about in the later part of the talk. They've been used for insulating by various space agencies, including NASA's rover, Mars rover, and for building insulation, which we will also touch on in this talk. Structurally, NASA used them to collect dust. Because of their porosity, comet dust particles could impinge on the surface, and instead of burning up on the surface, could be captured within the aerogel. They then brought this stardust array of aerogels back to Earth and had a citizen science project where one could be trained online and then go looking for particles. And actually, one of my collaborators did that, and she found a particle which gave her the naming rights for the particle. They can be used for chemical sensors. Again, if you have a high surface area, that is a big advantage for things like sensing and catalysis. And there's considerable work in my group that has been done in both of those areas, but I'm not going to be touching on that today. We initiated aerogel research at Union College a little bit more than 20 years ago. I've been on the faculty at Union since 1992. And as the introduction indicated, I'm an analytical chemist by training. My colleague, Ann Anderson, in the mechanical engineering department, also coincidentally started in 1992. And in 2001, a student, Ben Gothier, came to her. He had seen this fairly famous NASA photograph, sometimes called the Mona Lisa of aerogel photographs from NASA, that shows a silica aerogel and a flower on top of it. There are also photographs with things like chocolates or crayons, things that would normally melt, and a big source of heat underneath, illustrating the really impressive insulating properties of this material. And he said, I'd like to make one of these for my senior year, my fourth year project. And Anne, whose background was in heat transfer and fluid mechanics, among other areas, more or less said, well, then we'd better talk to a chemist if we want to make something like this. And so she sent the student to me. And I was already working in the area of chemical sensors. I was already working with sol-gel materials, so I was familiar with the literature on this. And I told the student that, yes, I know what aerogels are. I think that they're really exciting materials and very interesting. I would be particularly interested in using them for sensing because I had recently read this article that came out of a collaboration between Nick Leventis, who at the time was at the University of Missouri-Rolla, and Deborah Rollison at the U.S. Naval Research Laboratory, that showed that they could modify aerogel monoliths with a fluorescent moiety to sense oxygen close to the speed of open air diffusion. And so I had been really excited about this possibility. But as I mentioned to Ben, we did not have the equipment on campus to make aerogels via the conventional method. And so in the next few minutes, I'm going to talk about standard ways that aerogel materials are made. And again, I'm going to focus on silica aerogels, though there are product. So one can also then subsequently react those hydroxyl groups with either other hydroxyl groups or with methoxy or ethoxy groups and start connecting together to make an overall backbone of silica. And so this is just a standard approach to doing this, right? We're now having the condensation reactions that are connecting together. Those condensation reactions could split out methanol or ethanol or some other alcohol, or they could split out water if we have two hydroxyl groups reacting. So I'm an analytical chemist. I am not a synthetic chemist, but this is synthetic chemistry that analytical chemists can do. So this was something where I was comfortable going into that. I was already making sol gels with my students and entrapping fluorescent and phosphorescent probes in them for sensing applications. The difficult thing about making aerogels is not making the network, the solid network. There's a lot of established chemistry for that. The difficult part is drying that gel without the pores collapsing so that the pore structure remains intact. So if we think about this cartoon of a wet gel here, we have formed colloidal particles. In this case, we're talking about silica particles, colloidal particles of silica. Those particles have connected together to make an overall solid matrix that extends throughout the container in which we've made this. And the pores of this material are filled with solvent, excess solvent from what we started with, because recipes typically involve starting with alcohols or an alcohol and water mixture in order to solubilize the alkoxy precursor, and also the solvent byproducts, which are typically the same solvents of the reaction. So if we were using tetramethyl orthosilicate, the solvent mixture would be methanol and water. If we were using tetraethyl orthosilicate, the solvent mixture would be primarily ethanol and water. And so we have this solid matrix. If we can remove the solvent without the matrix collapsing, then we have an aerogel. And the aerogel by volume will be 90 to 99% air. If, on the other hand, we let this material dry under ambient conditions, if we let the solvent evaporate, the solvent evaporating will cause issues with capillary action and surface tension and collapse to some extent the pores, leaving us, if we let it dry all the way, with a xerogel. This is a Greek prefix for dry gel, that still is porous, but has a collapsed porous structure. And so the difficulty is getting the solvent out without having pore collapse. Now, there are three general approaches to doing this, right? Essentially, what we're having is, if we think about just a generic phase diagram, where our liquid-gas barrier, if we try to go over it directly without any sort of modification, we're going to have, as the solvent evaporates, we're going to end up with capillary action, surface tension, and pore collapse. And so we're trying to avoid crossing this boundary. Now, one possibility is to do a lot more chemistry and to surface modify the matrix so that it has very low surface tension. And so if we put some sort of agents on it so that it has extremely low surface tension, we can do ambient pressure drying, and you will still be left with an intact aerogel. This requires, as I said, more chemistry and a certain amount of patience. Another possibility is to cool down the mixture, drop both the temperature and then the pressure, and freeze dry it. And this method allows you to make generally powdered aerogel materials. They generally don't stay as an intact monolithic species. And the other option, which is the most common way of making them, is to use some sort of pressure vessel and take the temperature and pressure of the wet gel above the supercritical point of the liquid mixture that's in the pores. If we're in this region, the pores are filled not with liquid, but with supercritical fluid. If one then releases the pressure, the fluid escapes without causing pore collapse, and the material can then be cooled down, and lowered the pressure and cooled down, and one is left with aerogels. So if one wants to make monolithic or single piece large aerogels, the supercritical extraction method or the ambient pressure drying method are generally the ways to go. And the supercritical drying, because of the temperature pressure conditions, generally what's done is that we start with the wet gel and we exchange the solvent in the wet gel for liquid, and so in a pressure vessel, for liquid carbon dioxide. This will generally require multiple solvent exchanges because the solvents in the pores are quite polar and carbon dioxide, of course, is not. And so a series of solvent exchanges, typically to go to a more non-polar liquid solvent, then in a pressure vessel to go to liquid CO2, are performed. And then in that pressure vessel, something like an autoclave, the temperature is brought and pressure are brought above the supercritical point of CO2. And that is the method that I was most familiar with, but we did not have a critical point dryer or an autoclave that we could use for this purpose. I need to say a little bit about the institution at which I teach, because it's a very different sort of institution than exists in a lot of different countries. In the US, there are quite a large number of what are called liberal arts colleges, which are schools that offer the bachelor's degree only. We have no graduate students. Union is a fairly old institution by US standards, not a very old institution by standards in certain other places of the world, established in 1795. And we have students that study all different subjects, from arts and humanities to social sciences, science, and engineering. And having engineering is a little bit unusual, even for a school of this type. We're also a private institution, not a public institution, and so we are not funded by the state of New York or directly. And we have only about 2,100 students and about 200 faculty. The faculty are expected to be research active. We are expected to expose our work to peer review and to be doing high quality research, but we aren't expected to have the quantity of research that one might have if one had, for example, 8 graduate students and a couple of postdocs working in the lab. And so we do have significant resources for research, but we just didn't have a critical point dryer available. And so over the course of the next year and a half, working with undergraduate students, Anne and I came up with invented a different way of making aerogels. And we based it on some papers we'd read coming out of Lawrence Livermore National Laboratory on rapid supercritical extraction methods, which extract the solvent in the pores, whatever that happens to be. So in our case, alcohol water mixtures, directly without doing solvent exchanges. The method that we use employs a hydraulic hot press. And at this point, I should say that a laboratory scale hydraulic hot press is actually considerably more expensive than a small autoclave, but we had one of them on campus. So we had access to a hydraulic hot press because it was used in a mechanical engineering laboratory. And so what we do is we form the gel within a confined space in a metal mold, and we put the metal mold into a hot press and then close the platens of the hot press around the mold using suitable gasket material. So typically graphite and a metal foil. So the precursors are put in, we close it in place, and then we use the hot press to drive up the temperature of the platens, which drives up the temperature in the mold. And in the next slide, I'll talk you through the process in more detail. We have published and patented, and we have a video article that shows how this method works. We use it to make intact monolithic silica aerogels, although we can also make aerogels of other types. In short, we close the mold in the press. We start to heat the press, which heats because the mold is made of metal, which increases the temperature of the mold, which increases the temperature of the contents of the mold. And because it is sealed by the pressure of the hydraulic hot press, it can't escape. And this drives up the pressure within the mold. So we increase the temperature and pressure until we are above the critical point of the mixture that's in the mold. We let it sit for a little while, and then we release some of the restraining force, which allows the supercritical fluid to escape. And we do, of course, have this vented, which is not typically how the hot press would be set up. We then cool down the mold, which cools down the contents. And so if we look at a pressure temperature trace, this is the green line is the methanol liquidus line, so the liquid to gas transition. And what we're seeing in red is experimental data where we start at room temperature and pressure. We start increasing the temperature, and as we increase the temperature, the pressure increases, and you can see that we get above the critical point. We release. Now we have a very hot aerogel, and we cool it down, and then we have the aerogel. So we have recently published, I think it's available online, not yet in the print version, a retrospective article on the 20 years of work that we have done with this method. Now, silica aerogels can be made with a really large variety of starting materials, and this is one of the reasons that they're so attractive for the building insulation application. You can use the alkoxides that I was talking about, TMOS and TOS. You can use organically modified ones where one or more of the branches has an organic group that's not able to participate in the hydrolysis and condensation reactions and therefore remains trapped within the material, giving it hydrophobic properties, for example. You can also use salts, and you can also use certain types of waste materials that are high in silicates, including fly ash. And so for some of the applications in building materials that do not require translucency, a big advantage is that waste materials could be used to make these. And I didn't mention in the earlier process, but in order to do the hydrolysis reactions, you have to do acid and or base catalysis, which you choose changes somewhat the optical properties because it'll change some of the microstructural way that it forms. But there's lots and lots of literature on silica sol gels and silica aerogel materials. So I want to talk now about the application that we're focusing on in terms of building insulation for sustainable buildings. And because I'm in the US, I'm going to talk a little bit about just residential and commercial building energy issues in the US, but this is, of course, a fairly universal process. So these numbers are from the US. The issue is that building sector accounts for a very large percentage of electricity use and a substantial percentage of primary energy use. It's also a source, therefore, of greenhouse gas emissions. And so as we try to go to more of a zero carbon economy, this is clearly an issue. Now, the major issues, of course, depend on the climate. And in the United States, there are quite a variety of climates. I'm in what's called upstate New York, where we have all 4 seasons. So we have winter with a substantial amount of snow. And then we have summers where the temperatures do not rise as high as they do in the host of this webinar. In India, of course, the temperatures would normally be higher, but we can, routinely get up to 30 degrees C in the hot weeks of the summer. And so heating, ventilation, air conditioning are big uses of energy within the US for buildings. Major appliances as well. And one of the issues with heating and cooling is that whether a building is a residential building or a commercial building, we predominantly want to have buildings with windows. It's good for people's health. It's good just to be able to see outside. But windows tend to be very lossy in terms of energy, whether we're talking about losing heat energy or whether we're talking about having to use more energy for air conditioning because we are losing to the atmosphere. And so to the extent that one could insulate buildings better, can save a substantial amount of energy, and that can help move us toward really important goals in terms of energy conservation and sustainability. And aerogel materials have been used in a number of building applications. I'm going to point out the Springer Handbook of Aerogels, which has just been published, 2023. There was an older version of this from several years ago. This one is now available. And chapter 48, Aerogels for Super Insulation, I've taken these photographs from it. And so blanket types of aerogels, so fabrics that are impregnated with aerogels, can be used for building applications in lots of things. So around windows, or where you have a part of the building jutting out, or even for wrapping heating and air conditioning ducts so that you avoid losing heat as you're transferring it, or losing the air conditioning cooling as you're transferring it through a building. It can also, aerogels of certain types can also be mixed into plaster. And then this is a plaster application in Europe on the outside of a building to make a plaster that's more highly insulating than it would be if it didn't have the aerogel material in it. And this figure shows some other applications. Again, plaster sorts of applications on the outside, bricks, sort of brick aspect filled with aerogel material. Aerogel granules, these are translucent, not transparent, that could be used for daylighting applications. So in a situation where you have an atrium in a building, or maybe with a swimming pool or a gymnasium or a hotel where you'd like to bring diffuse light in. And so there are commercial products in these areas. Now, one of the things that I wanted to point out is that there are a lot of people working in aerogel materials for different applications, including building applications. And the major aerogel suppliers, again, I'm focusing on the US in this talk. Cabot has been making Lumira and other products that involve granular aerogels for quite a number of years. And some of the work in the skylights and the translucent lighting, a lot of those use granular aerogels from Cabot. Aspen Aerogels is another company that has insulating material, and they have made materials for things like super insulating coats and for blanket insulation for pipelines and things like that. And then there's the Aerogel Technologies is working actually with polyimide-based aerogels. These are not translucent, and so they're suitable for certain sorts of applications that don't involve windows. There are also lots of startup companies. And again, I'm showing a chapter from the new, I've gone too far, from the new Handbook of Aerogels. And each of the sections in here is a short description of various companies that are working. And I want to point out a couple of relatively new companies. Aerogel, which is in Belgium, is working with granular materials that can be put into plasters or flooring, when you're pouring a floor that has a resin-based floor for insulating things. And the three companies that I'm on the side here, Sun-Through, which is actually my startup company that we developed out of Union College, TM Factory, which is based on Professor Naganishi's work at Nagoya University in Japan and is in Japan, and AeroShield, which came out of the Massachusetts Institute of Technology and is in Massachusetts, are all looking at making, among other things, making monolithic single-piece transparent aerogels for inclusion in window projects. And each of us is working on trying to make bigger aerogel monoliths so that the monoliths are large enough to be used in normal size windows for buildings. So these are all areas that we're working in now. And so I'd like to emphasize something that's different about them, and that's that those three companies, Sun-Through and AeroShield and TM Factory, are each using different drying methods. So again, our method is the rapid supercritical method with the hot press, mixing chemicals, putting them into a mold in some sort of contained mold within a hot press. And so we're based on a rapid supercritical extraction method. The group in Japan is making gels, allowing them to age, doing solvent exchange and surface modification and ambient drying. And they are, frankly, able to make larger monolithic aerogels than we are, but to make a very large monolithic aerogel can take as much as a month, whereas our method takes on the order of hours. The AeroShield process is based on a more traditional sort of autoclave-based system, where again, they're mixing it together, letting it gel, doing solvent exchanges, and then doing supercritical extraction in very large autoclaves using CO2 supercritical extraction. We are all making monolithic, highly transparent aerogels, and the question is, can we make them large enough in a method that is suitably aligned with manufacturing to allow this to enter the market. So what we're seeing with our own work, and I'm going to talk now about work we have done at Union and in conjunction with our startup company, Sun-Through LLC, which has been incubated at Union, is looking at scaling up of the process. And when we first started making this, we were making small aerogel monoliths, small cylindrical aerogel monoliths. We were using them for things like sensing applications and looking at fundamental studies, and we didn't need larger ones. And we initially thought we might not be able to do it. So we started by putting support structures in. This is a metal aluminum structure. This is not what you would want to have in a window application because it would allow for heat transfer very easily. But we started with that, and then we realized we could make this. Now, we're in the United States, which means we use sometimes ridiculous units. So the hot press is an engineering piece of equipment. And so the window industry is also going to use inches. So you are going to see some inches instead of centimeters in here. We've been able to make some small prototypes. This one involves 4 aerogel monoliths sandwiched between 2 pieces of glass in a frame, and you can see that you can see through it with pretty good optical clarity. It's not as transparent as the window glass that's right next to it, but the thermal performance is very impressive. And so just to orient everyone, as the U value decreases, insulating performance increases. And a basic double pane window with air in the center has a U value of about 2. And so with the metal inserts, of course, we were getting thermal bridging, so that is not very impressive. But just putting a piece of monolithic aerogel about 12 millimeters thick in between the pieces of glass drops the U value by almost a factor of 2. And if we then pull a vacuum, as you may know that some window products, double pane products, they pull vacuum in between the panes to increase the insulating. If we do that, the insulating properties improve even farther. And so this was very encouraging, and we are working on scaling this up further. We've also been working on both with Sun-Through, which is our startup company, and in an academic collaboration with Professor Cinzia Barati and the rest of her group at the University of Perugia in Italy to look at the optical, the acoustic, and the thermal performance of prototypes made with these. And so these are 30 by 30 centimeter prototypes. They're not the prettiest prototypes. The purpose was to get them to a size where we could do some of the thermal and optical testing in using standard methods. And so at this point, we were just tiling individual pieces of the gel. We can see that the U values are just below 1. And so these are functional, but they're not as attractive as you'd like them to be. You can see that they're not as transparent as we would like overall. And so if you'll excuse me for a second, I'm just going to take a drink. Okay, and so we have had some funding from the New York State Energy Research Development Authority, again, because of the real promise for some of these materials. If we could introduce these into commercial window products, we could get performance more like a triple pane window without the extra weight and the size of that. And so that's the direction in which we're going. We've done work with looking at the effect of the chemical precursor recipe on the transparency of the resulting material. And here we're looking at percent transmittance as a function of wavelength. And we can see that by modifying the recipe that we use, still using the same starting materials, but changing the ratio, changing the amount of catalyst, we're able to get to more and more transparent, and something that will not be a real surprise to anyone if we go to thinner aerogels, even with the same recipe, because the path length is shorter, the amount of scattering that occurs would be less, and the translucency can go up. And so if we go down to about 3 millimeter aerogels, what we can see is that these numbers over here are average percent transmittance from 380 to 720 nanometers, and we can get up to 94, 95% transmittance, which is comparable to optical glass in the visible region. And so by going to thinner aerogels, although we still have good insulating properties, we're able to increase transparency. And this is a prototype from Sun-Through that has a glass, a little bit of a space, a thin aerogel monolith, another space, and the other piece of glass. And you can see that the transparency is outstanding. And I will say that AeroShield and TM Factory are also making thin aerogels with very high transparency. So all three methods work. It's a question of what's going to make sense in terms of an industrial product long range. Another thing that we have done a fair amount of work in recently is taking aesthetic approaches to aerogel materials. If you have a regular window, you expect to be able to see through it with a good optical transparency. But if you have, for example, a stained glass window, you're not necessarily expecting that. And so the imperfections become part of the design. And so the ability to make intact, perfect monoliths is not as important if you want to do something like that. We've also shown in work in collaboration with the aerogel artist, Yannis Michalotis, who's from Greece and is at the American University in Cyprus, that we're able to etch designs. And we've also shown that heat treatment can improve the clarity of some of these materials. So we've been working in a number of different areas focused at trying to get better aerogel materials for eventual implementation in commercial window projects. Now, as I mentioned, we're an undergraduate institution, and so all of the work that we do is done by faculty in conjunction with undergraduate research students. This is a photograph of our group when it was probably its largest size just before Union had to close for the pandemic. We have students from all over the United States, and we have had quite a number of international students work in the group as well, who are students that come to Union for their undergraduate work from other countries. Our work with aerogels is in a lot of different areas. As I mentioned, we developed a new method for making aerogels, and so that led to a whole bunch of fundamental studies to study the process itself. And we're looking at gas flow through aerogels for both our work with sensors and catalytic aerogels. We're doing a lot of work. Another sustainability area is in catalytic converter technology. And so we've had a fair amount of work in that. And we've done a lot of work with silica aerogels for a number of applications, including what I spoke to you about today for the buildings. Also drag reduction and gas sensors. We have established a laboratory, which is a collaborative laboratory on campus that involves some of the equipment specific to this, including the hot presses, instruments for measuring surface area and porosimetry, and we use other characterization instrumentation that's available within the science and engineering departments at our institution. And so this just shows some shots from the laboratory with some of the students working in that. We've been fortunate to have some wonderful collaborators. I mentioned Chenzia Barati, who is shown here at the right, with my colleague Ann Anderson and myself at the University of Perugia, as well as additional collaborators of theirs from other parts of Italy. The artist Yanis Michalotis, our colleagues at Sunthrough, who in fact are former students of ours, are running the company, and Professor Brad Bruno at Union, who's worked very closely with us on all of the catalytic work we've done. We have had, because the students are bachelor's degree students, they are not in the lab for a very long period of time. It might be a summer, it might be a year, occasionally as many as 3 years working part-time. So we've had a lot of students. We've had more than 170 students involved in aerogel research at Union since we started collaborating in the 2001-2002 academic year. We have had a substantial amount of funding, some of it from the internal sources, but a lot from, so a lot of sort of the seed money for the work we did was through Union College faculty and student grants. We've had a substantial amount of funding from the National Science Foundation for the fundamental research that we've done, and for tech transfer related activities between Union and Sunthrough. I mentioned the NYSERDA, which is a New York State thing, and both Ann and I are members of this Fulbright Specialist Program currently for the next couple of years. And I want to thank the audience members for attending. I'm very pleased to be able to speak to so many people remotely today, and I'm looking forward to questions. And I want to extend my gratitude again to the ACS Science Talks team for organizing this very enjoyable event. Thank you.